Hi everyone.
So today for the first tutorial, is this on?
Yes.
Yeah. Today for the first tutorial, we want to walk people through the use of Lorraine, which is still probably the leading method for constructing binary neutron star initial data in numerical relativity. It has additional functionality, but it's always been kind of one of, if not the leading option for the neutron star data in particular. I should say right off the bat that a lot of the work you're going to be hearing about today was done by my students, Gupte, who's a PhD student here at RIT, and Grace Fiacco, who's a physics undergraduate, who's been working with us as well. So much of the credit really should go to them. We're also working with a student from University of Rochester who couldn't be here right now. So before we show off how to actually use Lorraine, it's probably worth explaining a little bit about the underpinnings of Lorraine, just so everyone's on the same page and just to get an idea of what's going on under the hood. Cool. So Lorraine is a fairly well-established code by now. The original work dates back about 2001 for Lorraine. It is a multi-domain spectral method solver that basically can be used to solve elliptic equations, typically. The multi-domain is slightly different than things like spec in ways that are worth emphasizing a little bit later. It's particularly good at generating physically realistic binary neutron star initial data, among other things. The reason we're talking about it here is that while it's not part of the Einstein Toolkit, there are interface routines present in the Einstein Toolkit that can basically take Lorraine data as a starting point for launching further jobs. So a little bit about the Einstein Toolkit interface. Lorraine is not really, it's included as a library within the Einstein Toolkit. You should never really run Lorraine from inside the Einstein Toolkit. It's got the same issue, for instance, that two punctures does. These codes are giant linear algebra solvers that are typically serial codes. You can run them in parallel by basically letting all your other processors go to sleep. So while it hasn't been ported over, that's not really a problem. The data routines are present. But the code itself is fundamentally serial and should basically remain that way for the foreseeable future. It never takes so long to generate data that it's worth really futzing around with this particular part of the code. Like a lot of initial data solvers, it does use some kind of grid-based technique, but the grids are fundamentally different than the grids used by the Einstein Toolkit. So there's always some kind of interpolation step at the interface layer. The one good thing, of course, that is present for this, as well as two punctures, as well as many of the initial data routines, it means that you can change the resolution in Einstein Toolkit for the exact same physical configuration, if that's the problem you're interested in. For more information about the Einstein Toolkit interface, which we're not going to have time to go over today, there are several thorns in Einstein initial data within the Einstein Toolkit, and it's a little bit hard to see in blue on orange, but there is specifically a page on the user documentation designed to get people up and running using SimFactory to run a binary neutron star merger using existing data with all the documentation that goes along. So, like I mentioned, Lorraine is a pretty well-established code by now. The key papers for binary neutron stars and binary black holes date back to 2001. So it's been out basically for about 2 decades now. The neutron star work still kind of remains largely how people experience the code. It can solve for irrotational or synchronized neutron stars. Irrotational are now basically universally acknowledged to be the physically interesting case. So the vast majority of the work goes into that now. The original paper looked at polytropes. There's been quite a bit of work since on putting in different equations of state. So basically, different pressure prescriptions with respect to density. The black hole work is interesting, but hasn't been followed up quite as much. Lorraine's binary black hole solver is an excision-based black hole treatment. It hasn't been used as widely lately from what I can tell. It's largely been moved to the side by two punctures and a lot of the work related to two punctures. It's worth noting that you can actually set up a version of Lorraine that deals with puncture black holes. It's not clear that it is any particular advantage over the existing two punctures code, but in some ways it's actually a little bit easier to deal with after a while than two punctures is. It's not clear that you get any particular significant gain in accuracy, but it can be done. The least utilized part of Lorraine, but one I would think is going to make a comeback pretty soon, would be the black hole neutron star type work. There is a small amount of published black hole neutron star data. Again, excision-based black hole treatments rather than puncture-based. But in a series of several papers now 15 years old, there are black hole neutron star data that can be generated and used for simulations. As far as I know, LIGO thinks it may have seen one last I checked, according to the public archive. I would be surprised if more about this wasn't heard about at some point. Before we go on, this slide in its own way kind of explains why Lorraine initial data has always been popular. So this is just kind of a convergence plot. The VRL theorem is being used as a measure of error in initial data. And the key thing is that the bottom row, if you take a look, the y-axis is 10 to the minus 12 or so, and that's 33 by 25 by 24, which, if math serves me, is about 25,000 points to get an accuracy of 12 digits. You're not straining your laptop, and you're well past single precision and on your way to double precision. When Lorraine works well, these methods are spectral methods are accurate in a way that purely grid-based methods basically can't typically hope to. So before I hand off to my students who will explain how to actually use the code for real, I want to basically explain for anyone who hasn't had a chance to use it before the kinds of equations Lorraine solves and a little bit more about how it solves it. These are intended to look a little bit horrible, but not so horrible, if you've seen the Einstein equations as implemented in VSSN. It's not so much worse. Lorraine is, at heart, typically used as an elliptic equation solver. The top equation, the key thing is that for all the terms on the right-hand side, that's a Laplacian equation. That's not so difficult to solve. There's many techniques out there. There's the possibility of solving things that are slightly more complicated than Laplacians through numerical tricks, which are well established. If this was all it did, it would be a little underwhelming. The key thing is that it can also solve matter-based equations. And in particular, it can account for the fact that neutron stars have an edge where things are not smooth, and it's kind of built specifically to handle that particular case. So, next. So this one slide is basically the guts of Lorraine, and then I'm going to leave handoff. On the bottom, there's a picture that's possibly a little misleading, but hopefully not. The bottom is supposed to be the depiction of two neutron stars and the domains around them. Lorraine is a spectral method solver, so these are the collocation points for a fairly low resolution run, showing one domain on the inside, which would ostensibly be around the neutron star in each case, and a second domain that goes around them. The key thing, as you're going to see later, is that this is not where the domains end. Lorraine is a multi-domain spectral solver where there's two independent sets of nested domains, each of which covers all of space. So every point in space finds itself in one set of domains centered on the first neutron star, and one set of domains centered on the second neutron star. Apologies to those who have heard this kind of talk before. But in that sense, it's very different than a code like spec, where there's a single set of domains covering all of space once. The solution technique used by Lorraine, the basis for the iterative solver, is to solve for everything around star 1 and then everything around star 2. Ideally, the non-smooth behavior is localized to a domain edge, and you can avoid all the problems associated with Gibbs phenomena when you do spectral methods, or as much of it as possible. The way they do it is basically by breaking the source terms as much as possible into sources that owe their contributions to each individual neutron star. So, for instance, when you're solving for what I believe is the lapse, or some variable related to the lapse function, you try to localize the sources for lapse 1 to neutron star 1, when possible, its density, its energy density, etc. Those would be the A's in brackets here. But in order to self-consistently solve for things, you do get contributions from the other star. You can't do relativity strictly by straight superposition. It's a little nonlinear, as we've all found out. So you have to include contributions from the other neutron star. And this is basically done by taking a spectral expansion of one field at the collocation points of the other and reading it back in to the other star. When you work with Lorraine, you never need to think about this essentially at all. This is the part that's under the hood, much like these days for most users of the Einstein Toolkit. Virtually every cactus-based operation is also under the hood. But in some sense, this is basically the quick and dirty description of what goes on under the hood of Lorraine, and it hopefully will allow us to focus more on how can we use the existing tools that are out there to actually generate binary neutron star data that could then be ported into the Einstein Toolkit and evolved dynamically.
Thank you, Josh. I am Tanmay. I'm Josh's PhD student, and I'll be going over what all parameter files or like the initial setup of Lorraine that you need. So most of the public Lorraine data involves polydrops, where the pressure is a function of density and adiabatic index. But in Lorraine, there are tabulated equation of states, where you basically have a table where there are a bunch of numbers for different equation of states, which you can use. Or there is another way of doing the equation of state, that is by assuming that the neutron star is a piecewise polytrope. And there are several well-known physically motivated models for many equation of state. We have tried APS, FPS, and SLY. And there's a link to a paper which will give the information that is needed to code different equation of states in Lorraine. And it is parameter file driven, and most common choices can be utilized with minimal coding. So this is a piecewise polytrope generator. This is a piecewise polytrope equation of state calculator, which is an Excel sheet, and you need 4 numbers to get the table. The 4 numbers are in the yellow boxes, and eventually the number that you have to put in the table, which I'll show and things will become more clear, is the one in the green one, and it is there on the release notes. Okay, so for example, if you want to use SLY as your equation of state, then you need to put the first three numbers, that is log P1, gamma 1, gamma 2, and gamma 3, which are the 3 adiabatic indices used to describe the piecewise polytrope. steps. It first determines the center of rotation angular frequency so that the enthalpy is maximum at the center of both the stars. And this is not always stable, especially if the configuration, the initial configuration that we start with, if it is far away from the equilibrium, we have faced issues where there were wild oscillations occurring early in the process as the stars relax from spherical to tidally distended. And there was a potential bug in the original Lorraine code for which we had one-line patch, but before we patched it, we were not able to get stable configurations for unequal mass neutron stars. Secondly, it solves for velocity potential, and it uses to calculate the central enthalpy. So this method, so Lorraine has it uses various relaxation parameters where it averages over the new solution and the old solution, especially for step number 2. It reconfigures the domain containing the neutron star to map onto the new surface, and it computes the new metric fields, which are essentially lapse, shift, conformal factor, etc. So, what are the parameter files that are required? You need to learn Lorraine, you need to run 3 executables. The first one is init bin. So for init bin, you need the power EOS, which gives the equation of state model, and the power grid, which gives the grid dimensions and domain radii. So this is the equation of state piecewise polytropic file that we use, where the first is the number of polytropes, and the 3 numbers that we have to put from the paper that we showed are these 3 numbers, and the third to last pressure is this 1 number. So these 4 numbers we have to put in, otherwise all the rest of the numbers remain the same. So this is a typical equation of state file involving a piecewise polytrope.
It should be noted, hopefully everyone got the email. They're on the Google Drive for the workshop. We uploaded examples of just about all the files that you're going to see today under, I think it's Lorraine files. So there might be a little bit of renaming required, but essentially examples of all the basic driver files we believe are there.
Sorry, where is that?
So there's a Google Drive for the workshop that Joseph emailed about yesterday. If you go to that Google Drive and look under Lorraine files or something like that, it's basically got, I think, examples of all the things that we're going to kind of bring up on screen today. Yeah. If there's a question about any of the files we showed, these are all basically public files. It's just a matter of kind of getting them all staged so that everyone can see them. But yeah, I think we uploaded just about a complete set of things that need to be changed with respect to what comes in the documentation.
So this is a typical grid file, and you can change the numbers depending on whether you want a high resolution for your grid. And most of the terms that are used are, the definition of them is given. And you need one more file to run in a bin. So this one, this is the most important one, because this is where you mention what the central enthalpy of both your stars is going to be over here in these 2 boxes, and that you can get using a TOV solver. Like, we have built a TOV solver where it spits out different baryon mass and gravitational mass for different values of enthalpy. for a given equation of state. So using that TOD solver, we put in the center enthalpy corresponding to the baryon mass that we want, and then you run init bin. This part doesn't take a lot of time, barely less than a minute. And at the end of this, it even shows up what the baryon mass for each of the stars is, which will be useful in putting in the next step for running the coalescing sequence. So init bin generates these two files, three, calcul.d, identif.d, and ionide.d. After you have these three files, we run the whole sequence. Sorry, so I forgot to mention in par init you need this separation, which is just used for superposition. And the enthalpy that you mentioned is the logarithm of the enthalpy that we use. So the first one, init bin, after running init bin, you have to run the coal sequence, which is the coalescing. And for that, you need the parcoal.d file. So the first number over here is the separation, which is how much the separation should be between the two stars. And these two numbers, which you have to change, are the baryon mass, which is spit out by init bin. The other fourth number, which is important, is this one, which is the convergence factor that you require for converging the enthalpy, central enthalpy.
So, what do you mean by convergence factor that I require? What does it actually do?
So like if you put 10 to the power minus 7, it will just take longer time to converge. That would be the difference between the enthalpy stuff.
So it's an error that I get.
Yeah.
Maximum power that I'm factor.
And confusingly enough, it doesn't stop based on an absolute error criterion. It stops when the step-to-step difference falls below a certain value. What? So it's typically, so you can range on that value. There is the level at which it will kind of never drop below is something other than 10 to the minus 16. It tends not to converge absolutely forever. Part of the art of Lorraine is learning where is the noise level and making sure that your tolerance is set slightly above that. The other kind of random thing too, because it's set up to handle a relative change as the final difference, once in a blue moon it happens to get lucky, and some parameter tends not to change between two steps and it'll just kind of stop. But that's pretty rare. In practice, like a lot of spectral codes, you tend to, for every order of magnitude, each order of magnitude takes about the same amount of time to establish until you reach the diminishing returns point somewhere near the single precision level, at which point the code will kind of peter out and run as long as you let it, unless you move the tolerance a little bit higher.
I have a question about this. So in the init bin, you set the central enthalpy of the stars.
Yes.
Here you set the baryon mass. Those are both independent. Those are parameters that you could use to change the mass of the star, right? What if they're different?
So this is going to come up.
So these are the central enthalpy and the baryon mass uniquely define the mass of the star for different equation states. So how can you have both different
legacy Lorraine that we're kind of forced to deal with. So init bin is a little bit different than what one might otherwise think. So init bin takes basically two different solitary neutron stars and superposes them into a binary, but it never actually puts them into a real binary. It doesn't actually do the kind of the solution crossover fields and things like that. It's basically two superimposed spheres. At that point, the central enthalpy is a well-defined parameter, and if you take the central enthalpy for what's basically an isolated neutron star that happens to be living next to another isolated neutron star, a central enthalpy plus an equation of state gives you your respective masses, and they agree with a TOB solver when you check it out. We're going to get to this in a second. The coalescence routines that kind of actually treat the binary like a legitimate binary and then relax it into an equilibrium configuration. They chose as their convergence method that the key parameter is the baryon mass, and I mean there's reasons for that too. That's the more physical observable. So just like the baryon mass isn't one you can set for the initial state, the two baryon masses of the components are the variable you set for the legitimate binary, in a sense, to converge towards. And there'll be a note coming in a second. They kind of do a halfway scheme. For a user-defined number of steps, they actually keep the central enthalpy fixed and allow the binary to live within that, and allow the binary to relax under that condition. At some step, that condition is dropped, and all of a sudden it'll seek out the baryon mass and allow the central enthalpy to shift.
Got it.
But the code itself actually switches from one prescription to another by construction.
Okay, that's weird, but okay. So the baryon mass is the more important one.
Right. It eventually gets to that, but basically it takes its time getting there for reasons that I'll admit I've never fully understood.
Got it.
We have built what Josh said right now. We have built another routine called the coalescing sequencing routine, where the binaries start at a particular distance and eventually you decrease the distance by whatever number of steps or how much of a distance you want and bring them closer. So usually we started at 65 and then bring them eventually to 30, but it crashes before that. So the Lorraine units are sort of icky, and we had to construct a spreadsheet where we had to convert the physical units with the Lorraine units. Which looks something like this. Is just like a bunch of numbers using conversion factors. And you guys should also have one of these.
Basically, Lorraine is the only relativistic code in which I know in which big G is not equal to 1. Given a do-over, I think that would have been a useful switch. But the speed of light is equal to 1, but big G is specifically not. The secret to Lorraine is always the first time out. Make sure that, give it a configuration you're pretty sure you understand, and make sure the numbers that come out match up with what you thought you were going to get. It's hard to. I think big G turns out to be 0.01232 or something like this. It's far enough away from unity that you never get the right answer by accident. If you get the right answer out, then you have understood the units, but otherwise, it's easy to get it wrong the first couple times. One of the things we're going to be providing for Einstein Toolkit and whoever else, this should all be public, is just kind of, we have spreadsheets in place, we just need to kind of write up and document them. Just explaining some of the code conventions so that they cause less trouble for future users. The lore helps nobody in the field, basically. So want me to demystify parts that should never have been mystic in the first place.
So the issues that we faced while running Lorraine were the secant method failed for unequal mass binaries. Like it is used to locate the rotation axis of the binary system, and there is potential infinite divergence because you divide by 0 in the function being set to 0, and it continuously crashed. So we came up with a fix, which is it's given in the release notes. However, it's in the directory called this one given in the link, and the function that is used is double form binary, where the thing that we changed. So this was the function O2 star 1 minus O2 star 2. You just take the reciprocal of each of the terms, and that fixed the code for unequal mass binaries, and we are able to get data for unequal mass binaries after this fix. Another issue that we're facing right now is the center of mass and angular velocity. For generally high mass binaries, the routine used to calculate the center of mass and angular velocity has a tendency to wander, and it often crashes the code. Like you can see, for example, in this one it's not so bad, but in this one, this is a run where the stars are equal masses and at a distance of 65, and this is the center.
Unequal mass.
Sorry?
Unequal mass.
Okay, unequal mass. Okay, but not very different, right?
Very close.
Yeah, but it goes exceptionally close to one of the stars, which is not what should happen. And we are thinking of fixing it by implementing a variable mass sequence, where we slowly walk towards the higher mass binaries by using the relaxed configurations of lower mass ones.
All right, I'm Grace. I'm Josh Faber's undergrad. So, assuming that you have successfully downloaded the code, installed it, compiled everything, and can generate a successful run of pull, you can then make a bunch of plots that are shown up here with a program called pgplot under the executable litbin. I'll show you how to do that in a little bit. So Lorraine can generate these plots which show a bunch of characteristics about these neutron stars. Like you can see their positions on the grid on the top image over there, and so the green dashed lines, which are kind of hard to see on here, represent the two domains for the stars, while the white represent the